they think the Big Bang is how the universe began?
Yeah, absolutely.
And why do they do that?
Yeah.
Why do they think that for some reason the Big Bang is the origin of the universe and not the theory that explains the rapid the inflation of the universe after the universe began? Why would you think people kind of make that mistake and conflate the two? Tina?
I think it probably has to do with the name itself, because when you hear this terminology of Big Bang, you initially think, okay, that involves some type of force and it involves some type of matter. So that means that had to have what started everything that we know in existence today. And then they don't, unless you actually break it down and look at the entire scale of going from like also the dark ages and then into inflation and then into when everything actually started to form and galaxies and stars formed, then you see, oh, wait a second, this isn't actually like what, like you said, isn't really actually the origin of the universe. It's more of just an event that happened very spontaneously and quickly. And that's probably where the misconception comes from. It's just because there's usually a general brush over, I think, a lot of times, especially when it comes to, I don't know, maybe like shows and stuff like that. When they talk about the Big Bang, they think, oh yeah, that's what initiated everything. And that's, this is the origin of the universe. So that's probably, I think, why I get that a lot from people, because they think, oh, well, the name, it just says Big Bang. And that's usually what starts anything. As opposed to looking at it as a thing that actually was a moment, a point in time that initiated a growth after that. So that's kind of my viewpoint.
Just a misnomer in some ways, right?
Yeah.
Well, remember that the Big Bang term was originally coined by Fred Hoyle on a radio program to derive, basically as a mocking the theory, right? There was
right.
People were using terms like primeval atom or primeval nucleation or something of that form, and Hoyle sort of said, well, it sounds like they're trying to describe a Big Bang, right? And that was meant to sort of mock the thing, but that moniker kind of stuck, and so we talk about Big Bang cosmology.
Do you think the name will ever change? Like even generations in the future, a century later, it'll be have a better name?
Yeah, I personally do, because honestly, if they relate quantum mechanics to like general relativity, there's going to be something newer and bigger and better that comes out of these theories.
Yeah, I remember Brian Cox called it a everywhere expansion.
Everywhere expansion.
Yeah, but again,
yes, that's a good one. Yeah.
So the theory talks about that our universe began in a hot, dense state, and is still expanding after its initial event, and the matter of the universe is approximately 80% hydrogen, 90% helium, 1% lithium, blah blah blah. It states things like that, but it talks about how the universe began, not what was there beforehand. But theories don't need to explain everything, right?
Right, and that's a good point. Even within the Big Bang theory, there are other theories to explain things, which we'll be getting into. Mm-hmm. All right, so the Big Bang basically explains the inflation of space-time, basically. Next slide. And by the way, don't forget, people, go sub to Athena while we're waiting for this. I want to see those numbers kind of go up, people. Okay, because in the video description, you can go to her link. Come on. We got like 200 people that can go right now and do it. So
I write out
Big
the
Bang and inflation. Yeah, I'm not kidding. Go check out her videos. I mean, you guys are gonna be impressed. So anybody can talk about wave function, you should be automatically a sub to. So this is where we start getting into the actual science, Big Bang and inflation, because if you look to the right, the Big Bang will show various epochs of time from the point of whatever it was where the universe began, where this hot, like you said, this hot, dense universe started cooling off, and you started having things like recombination periods where all these ionizations would allow for atoms to start being neutralized by protons absorbing taking electrons and making neutral atoms. This reionization is the opposite of ionization. And then obviously, they had matter forming, but you also had things like the quarks being formed and this gluonic soup and all this other stuff. But the main thing is that there was a period of time that was very, very short. I think it was around 10 to the negative 32 seconds, if I'm not mistaken, the inflation period. Somewhere around that ballpark.
It depends on that's one of the things that people are trying to determine, pin down, is when the inflation period started and stopped. But one of the important things to note, is it was mentioned also in the chat, is that the Big Bang starts out with a non-inflating universe, right? Inflation comes later. The Big Bang event, and then you get inflation, and then inflation stops or slows down.
Right.
Most Big Bang models that have inflation start with a Big Bang and then bring in inflation, and then inflation turns off.
So what was the main reason why they came up with the inflationary model to begin with? I have three different reasons, which we'll get into, which was obviously the cosmic horizon problem, the monopole problem, and the flatness problem. But why did we need to actually come up with something to explain these things away?
Well, okay, I'll jump in. One thing is that you see kind of a funnel happening here, and that's something that right now has been a way to sort of explain what we see currently happening in the universe. So coming from an observational standpoint, where we weren't around when the Big Bang happened, but we are around now, and we see everything around us moving away at an accelerated rate known as the Hubble constant. And so you see this constant expansion. So if you were to go backwards and rewind that, like as if you're rewinding, obviously just ourselves, then you'll start to see that obviously this is where right now we're in expansion, but that had to have retracted. And then you keep getting smaller until you get to the Big Bang. So for me, this is kind of a basic way to sort of explain that. I know someone can go into more of an elaborate way, like you said, bringing up the other models, but that's really where inflation came in, because it serves as a funnel to explain to the point that we're at today and then where we're going.
One of the things that happened early on with the history of this theory is that the assumption was that the theory states that the universe began with a hot, dense, uniform state. And the question that was asked is, well, how did it get to this non-uniform, lumpy universe that we have today? And they began to run into problems if they assumed that things just magically decided to clump up, because in that early universe, the universe was able to equalize. So if there was any fluctuation that caused some part of the universe to get hotter, the energy was quickly dissipated throughout the rest of the universe. The universe was compact enough that things could equalize. And then, but that's not the case today. And so inflation was an attempt to try to take Big Bang cosmology and actually put it on a sound footing with respect to the observations that we see today. Work is going on right now at the South Pole. There was an initial attempt with something called Bicep 2 that was looking at, supposedly they're looking for evidence of the effects of the in inflation state, and there were some problems with the data. In particular, there's some stuff that they couldn't rule out with regards to dust complicating their measurements. So Bicep 3 is being conducted right now, where they're using a multi-wavelength set of measurements. And when I was there in January, the people were very pleased with the performance of the instrument. Obviously, they're not going to reveal the data that they're collecting, but they say that the instrument is working well, and they're expecting to be able to have data to analyze on schedule.
Okay, I think that kind of works.
That data will help us understand. That data will help us understand things such as, for example, they're looking at the last time that photons bounced off of essentially gravitational waves that were in the early universe,
Now you're talking about the period of time where the universe was kind of opaque, and that there's just like a sea of electrons, light couldn't really escape,
Yes.
And then the recombination period happened. Electrons combined with protons to form neutral atoms, and then all that photonic energy that was there was allowed to burst out in a cosmic flash,
Yes.
And that's what we see now as the cosmic microwave background radiation. Correct?
Yeah, and yes, and those that last ricochet before the universe went transparent, imparted a particular polarization on that material, and so they're looking at that polarization, and there's properties that if we have these ways, for example, that LIGO was able to detect that were dominant in the universe, that were part of the result of the inflation period, then they should have these certain properties. So they're trying to detect the last ricochet before the universe went transparent and pin down perhaps when the inflation period might have started and stopped.
Okay, next slide, and then we're going to dive into each of these. Well, hopefully they always get good data. All right, so I call it the cosmic event horizon problem. You call it the horizon homogeny problem, or homogeny or homogeneity. How do you prefer it? I call it homogeny, but homogeneity. Okay. So horizon homogeneity problem. Basically, how could regions of space that are too far away due to the speed of light remain homogeneous effectively at the same conditions without some kind of mechanism that sets the same initial conditions everywhere? So when we look at the background radiation, why is it so similar with a very small temperature differential? Why are the constants the same? Why is the fine structure constant similar in all points in the universe? And I'm going to kind of let Dr. Kroon kind of jump in on this one. Why is it that we see a lot of homogeny in the universe, but we still see many things like answer entropies, which are irregularities in the cosmic microwave background radiation as well? And is that somehow set from whatever the initial conditions were of the Big Bang? Is that what we're seeing now the result of those things?
Yeah, kind of. Well, yes. But one thing that I did read about is how they were trying to look at variations in the speed of light arbitrarily far back in time to look for variations in any of the fundamental constants of the universe that dictate the speed of light, and other things such as the wavelength of hydrogen Balmer emission lines. And they found that essentially the speed of light has not changed. So it seems like the laws of physics and the constants of the universe were constant to a very high degree throughout the age of the universe.
So there's a natural relationship between all these natural units, right? So when you have like gravitational constant, you have like the speed of light, you have Planck's constant, you have the fine structure constant. There's a relationship between all of these, is there not? Such that if any one of them changed, all the other ones would change somehow, including the speed of light, because the speed of light is very dependent upon things like the fine structure constant, and as well as electric and magnetic permittivity and permissivity, right? So if we did have the speed of light change in the initial conditions, could it be feasible to even say that our universe would not be the way we know it now?
Yeah.
So a good thing that it hasn't.
The speed of light, which is dependent on the permittivity and the permeability of free space, would show up again in things like the fine structure constant, which dictates things about like the strength of chemistry, how chemistry happens that would affect biology, and molecular forces that bind comets and planets together under the action of gravity. There would definitely be a very different universe if you changed any of these by a lot or even a little.
Okay, so the inflation model was put out there to try to resolve this particular homogeneity. I hate this word.
Homogeneity.
I call it homogeneity.
I say it I say it the way you do. Homogeneity. I say it, but he says it otherwise. So I guess it's like potato. But it is homogeneous. So
I've heard when people say homogeneous that's wrong, that it's homogeneity.
Really? See, I don't. I guess
how much like what part of
you know
part
what?
of
I'm
my
going to go with
dissertation